Okay, thank you very much. So it's a great pleasure to come back at ICTS. This is my third time. Like even the friends who help things moving around, they know me and I keep chatting with them here. I really would like to thank the organizers of this workshop. So I don't see all of them here, but Shantanda is here. But nonetheless, let's add Santosh and Nihar in the list to thank them all and start. So I was asked to give sort of a semi-pedagogic lecture plus overview of application of machine learning in jet physics. So what I thought that in this set of lectures, especially the ones which Peter covered, we saw many different application of jets in medium and things like that. I come from a PP background, which means I work at zero temperature and all the physics relevant to zero temperature physics. And since I was asked to talk about machine learning connection with jet physics, I thought it won't be a very bad idea once let's go back to at textbook level and try to see what is our basic understanding of jets are, how do they form, and then try to connect why application of machine learning to such complex quantum mechanical object called jets are necessarily worthy. In order to do that, the first half of this lecture I will spend on how jets form, and we really need to understand that we cannot collect any arbitrary set of 4 vectors and call them jets. There is a very definitive set of 4 vectors which are combined through something called a jet clustering algorithm, and there is an underlying physics-driven motivation to even design such an algorithm. Given such cases, and the jet, which is essentially a set of 4 vectors, why it's worth connecting to machine learning is the part of this lecture. So please stop me at every level you want to. It's not important for me to read all the slides. Tomorrow I again have a slot, but nonetheless, it's important for me to clarify your queries. Okay, so let's move on. Since I'm an experimentalist, why we at all talk with jets, at least people like me, is the first answer is as following. Here what we see is very important. This is a little older plot. It's from 2 years back. There is an improved version of this plot, but nonetheless, this sort of gives us what are the kind of process LHC measures. We collide proton and proton, and the x-axis is something what all possible final states which we try to measure. And this is sort of a triumph of LHC. When we think of LHC, we always say, oh, Higgs was discovered, its couplings are measured. Of course, that's like the greatest triumph. But think of one machine which can measure numbers starting from 10 to the power 11, going to 10 to the power minus 3. So it's a huge range of variation of processes which a single machine can measure. Of course, it's done by different people. But nonetheless, I don't know whether you can read it. There are little subscripts here, which says you have final states, which are exclusives, but then on top of that, there are many different processes where you measure something final state plus 1 jet, plus 2 jet, so on and so forth. At least if you don't care about jets, obviously you people are not those ones. There are some, when I talk to people like who are interested in axions and things like that, they sometimes say we don't care about jets. You people definitely do in medium. But for me, as a person from PP collision sector, you see that there are so many processes which actually involves jets in the final states. And we cannot avoid that. Protons are mostly built out of gluons. All the PDFs, plots, which you have seen from Peter's talk, you saw that gluon PDF has a very large dominating contribution. Once you accept that, jets will be there in the final state. So there are no way we cannot understand jets and can keep doing hadron collision physics. So understanding them is absolutely important. Okay, great. So my first part of the lecture is about how do jets form in PP collision and not just stories, but to build a little semi-analytic understanding about if we see distribution at a later stage, how do we make any intuitions about them? So that's the first part. Okay. So let's say when we actually see in a collider, a phenomena, an event, these are the kind of energy deposit patterns do you see. Now, connecting this sort of energy deposit patterns to what we can compute starting from first principle QCD Lagrangian is actually a very, very rigorous and difficult job. So how we do that is something important to understand before starting. Let's say I'm given this part of energy distribution. Let's start doing machine learning on this. Before even starting doing machine learning, we really need to understand what kind of questions we want to solve using machine learning and why those questions make sense. So first, this is the direction I will try to venture with you, that what are the kind of questions we really want to understand and want to solve when we really talk about physics of jets. Okay, so let's start that. This outcome, like energy splash in colliders, what is our best understanding when we actually collide proton? The end state configuration is a bunch of hadrons, leptons, photons coming from pi naught decay, and prompt photons coming from QED Bremsstrahlung. Everything is present there. So if you think of what we see in a single event of a proton-proton collision, these are the set of final state particles we observe. And this set of particles are the ones which essentially enters in our calorimeter, deposits energy, and this is what we can measure. All the physics inference which we do is out of this measurement, and theoretically, we try to compute what will be the distribution of the particle. And the distribution, when I say distribution, it means both number distribution as well as their kinematical distributions. Great. So what is our understanding that how such a particle distribution configuration comes into the first place? So when you take the QCD Lagrangian, it says that there are interaction vertices between quarks and gluons. Gluons have self-interaction. Keeping this sort of interaction vertices in mind, this is the way which our understanding how a parton fragments. And then this parton gives energy deposits. So here, at this point, I want to make a disclaimer that those of you who were there in my lectures 1 year back in IMSc, you might find 7-8 slides which are sort of overlapping discussions. I apologize, but I think those points are very, very important when we try to address jet physics. Okay, so I will repeat those. Now, it's interesting to see that when we look about the growth of the shower, the parton fragmentation, they are not isotropically built in all directions. Rather, if there was a back-to-back quark-antiquark pair which were going about, the parton fragmentation are happening sort of in a collimated way. So do we understand this phenomena from first principle QCD? Let's try to understand that. All of this will play an enormous important role when we try to apply some task with jets. This is actually the quantum dynamics of a jet, which we really need to understand starting from first principle. So let's do it. The stream of particles which we get here has to be explained starting from this Lagrangian. Of course, I didn't put the gauge fixing term, ghost terms. All of you know that. Right, where it all starts. It all starts how a parton fragments. And for that, the most important textbook material, which we really need to relook into, that if we have a final state, let's say a quark line passing by and emits a gluon, you open your QFT book and write down the amplitude. And when you write down and apply all those kind of fancy spinous operation, you start getting something following. This is the amplitude, and the total amplitude has something, it's divergent. Now, here where things become really, really interesting, that I have summation of two diagrams, and if I do a mod m square of this, try integrating over phase space, I will get a divergence. So let's stare at this formula. If you ever solved Peskin chapter 6, you will hit this formula somewhere. Okay, and it's important to remember that whatever infrared divergence we get, it's contributed from the first term. If you integrate over this three-body phase space, over this particular term, the last two terms give you finite numbers. So the sole reason from where the infrared divergences occurs from this term. Okay, and how we actually tackle them is the core understanding and principle behind designing a jet reconstruction algorithm. So it's important to keep mind that infrared divergences are there. In QED, in QCD, we have to tackle them. Great. So let's spend a couple of more minutes, walk through the calculation so that we get our intuitions right, and all these ingredients will play a role towards designing the jet reconstruction algorithm. So what we have is a three-body phase space, and we effectively, when we start integrating over, what essentially we land up with is that the probability of a quark line emitting a gluon line has this structure that we want to understand that a gluon within energy E to E plus dE and at an angle theta to theta plus d theta, what is the emission probability? Whatever, if you even don't care about the rest of the calculation, it's necessary and sufficient to know that the probability distribution function is proportional to this part, dE over E multiplied by d theta over theta. So there are two such differential paths. Now, if you compute this from a gluon being emitted from a quark line, this CF factor comes. If you repeat the same calculation using the trilinear vertex of the gluons in QCD, there will be a factor of CA. For SU-NC class of theory, CA is equals to NC, which for our QCD, good old QCD, it's 3. And that's the formula which you really care about, that the probability distribution function of emission of a single gluon from either a quark line or a gluon line has this nice little structure. And when you look into this, you see that when we actually sum over the real emission diagram and the virtual correction, there is a cancellation. So you remember that if we go back to this set of diagram, all of you have computed that what corrects the charge renormalization, there is a gluon virtual gluon exchange. You have done this for the form factors of QED as well. And from the IR modes of this virtual particle exchange, there is also an infrared divergences. And these two pieces of infrared divergences exactly cancels to give you a finite cross-section. Okay, this is the core physics underlying. And when you replace the alpha s by a running alpha s, which you know by solving the beta function equation of QCD, the total cross-section is actually a scale-dependent number. If you, for a given process, if you measure the total cross-section, it will depend on scale. If you measure something at 10 GeV versus 100 GeV versus 1 TeV, the number, the absolute production cross-section will change, and that's at our phase. Now, why all of this is important for jet physics? We have a naive, intuitive understanding that if there is some pattern which is coming out as asymptotic states, it will form jets. But it's a little non-trivial than that. What do we actually mean by jet and how we relate it to a pattern is actually a bit deeper question than what we naively, intuitively think. So why that's the case, let's try to understand it. We just worked out that emission probability is proportional to dE by E times d theta by theta. So if we really want to compute total number of emission given an initial pattern has some given amount of energy, let's try to compute it. And when we perform this integral, we see that there is sort of a dependence of this sort, that there is a log square term plus order of something, which is alpha s times log. And when we plug all the numbers back, even without doing any higher order fancy calculation, just you put a piece of pen on the paper and do tree-level computation, it says that the average number of gluons which is coming out of a fragmentation process at tree level has some scale dependency. It's just a nice little formula. And if you take slow variation of alpha s, put it something like 0.12 or whatever, and plug the rest of the number, what you will get, this average multiplicity is 2. Okay, you can just plug some numbers. You know what is the value of CF, B0, everything is given, and choose a value of alpha s, 0.1-ish. You will get the number 2. What this means has a profound significance. It says you start with a quark, or even say a gluon, but what you will end up with, if you compute mass of that system, the mass is finite. So this naive interpretation that if one particle decays into 2, and if you do a combination of the kinematics and compute what is the invariant mass, the initial gluon or parton mass is likely 0. It's very small. For gluon, it's exactly 0. But what comes out of the fragmentation process, that thing has mass. So the fact that even light-flavored partons, the jets originating from light-flavored partons have mass, the source of mass is purely QCD fragmentation. Okay. Given this is the phenomena, we now try to understand, can we, and this is a mass we can measure through laboratory experiments. So given that we can measure mass, can we use this phenomena in order to identify what is the source of the partonic source of the jets, what we measure? Okay, this is our first sort of little 5-10 minutes discussion of how jet forms. Like, at least actually we haven't even discussed how jet forms. We tried to understand, following basic principles of QCD, that how parton fragmentation happens, and that gives rise to masses and things like that. Now, yes?
Because how do you choose Q0? What is Q0?
So it's lambda QCD, where this formalism, like below lambda QCD, you cannot treat the parton fragmentation as perturbative process. So you have to keep a minimum energy threshold from where you can do this integration.
So that avoids the divergence.
Yeah.
Can you give me a physical sense of why lambda QCD is, why you can ignore?
No, I can't. No, I can't ignore that. What the statement says, if I estimate the multiplicity of a parton shower and want to build a first principle method to analytically compute, what is the phase space regime over which my analytical computation is valid?
Okay. It's not a physical statement about the formalism.
Formalism, absolutely. So my formalism breaks down when I go below Q0. And similarly, the same scale Q0 puts an angular cutoff. Okay, good. So please stop me whenever you have a question.
So from that formula for the number of gluons, I guess, how you're saying that jets have a mass? I mean,
so let's say one parton fragments. Now you want to estimate what is the average multiplicity. The thing I was trying to tell you, you plug numbers here and take a rough value of alpha s, which is 0.1 is a good crude approximation over a wide range of scale. Now, you know the value of CF, B0, pi, etc. You plug in, you will see this number is roughly 2. Now, what does it mean? That average number of fragmented partons coming out of this is 2. So if you take 2 partons, take their 4 momentum, and compute an invariant mass, that won't come to be 0. Okay, that means if you really just want to do a relativistic kinematics and ask the question that what was the mass of the original parton, by using the formula of relativistic kinematics, the answer is non-zero. So this already tells you that when there is a parton shower and fragmentation, if you take the whole collection, the invariant mass associated with the process is non-zero. So, but your understanding of QCD says gluon has 0 mass. So if jets, what will be a collection of particles, how that forms is something which we will come to, that has a non-zero mass. And the real source of this non-zero mass is QCD partonic fragmentation. Okay, great.
Convert the virtuality that you gave us.
Absolutely. I just wanted to go back and address this issue from textbook level. Great, let's move on. So now these jets are best represented in.
All that you are saying is that the one that starts the jet is a virtual.
No, it's if a gluon starts, it's not on shell. Yeah, but let's say so it's an important thing to understand that here, when we will talk about jet, the jets will be formed by hadrons and not the partons. And even if you start with an on-shell gluon having 0 mass, the jets you will form will have a mass because during the process of hadronization, the low energetic partons will pick up from the zero temperature medium. Okay, so jet will have a mass. It's just important to understand that this sort of goes a little bit away from our understanding that like the kinematics would have given us exact 0 mass. That's not the case. So from where it's originating. Yes.
So what's the physical interpretation of Q in these formulas?
The Q is the scale coming from the RG running of alpha S.
Yes, but in the physical process, I understand what
Yeah.
Q is, but in the jet formation, I mean, what you said number of gluons, you put it in alpha as a 0.1.
Right.
That's a relatively large Q.
Right.
What process do you have in mind to choose a large Q?
So if a hard scattered parton is produced due to some scattering, the momentum transfer of the process is what my Q is.
But what's contradictory is if I now dial it down and I look at relatively soft processes, alpha S goes up, the number of gluons goes down. Okay, good. All right.
That's how it's like.
Okay, good. No, I had it backwards in my mind.
Sure, it's. Okay, great. Let's move on. Now the jets have the best representation, as per our understanding, is in something which is called Lund jet plane. Why? We went through this process that we discussed that the emission probabilities are something proportional to d by E times d theta by theta. Now, you can convert E to the fraction of energy carried by a parton. So the total energy cancels out from the numerator and denominator. So it's essentially d log of 1 by z, d log of 1 by theta. And where this emission is happening, that carries a whole lot of information. So in this plane of log of 1 by theta times this is KT, so which is essentially like the energy scale times z times theta. So it's a bit modified representation. Different regions denotes different kind of parton fragmentation. Here there is something called hard collinear fragmentation. When you come down here, soft collinear fragmentation, and different kind of partons, depending on their interactions, lies in different region. At least their primary emission lies in different part of this plane. So we will try to understand jets in terms of these diagrams, which we will address today as well, and again come back tomorrow. Okay, so let's keep this in mind. Already Peter talked about it, that Lund jet planes are important. I just wanted you to connect with the very basic textbook stuff, that why Lund jet plane is a very constructive way to look into jet physics. Great. So now we understood parton shower, but I started the talk with some energy deposits in my calorimeter and some charged particles bending in the tracker. So we really need to understand how do we associate this bunch of fragmented partons with the energy deposits happening in the calorimeter. Okay, this is a real interesting task, without which we, the experimentalist, can't survive. So let's address the problem. What is the problem we have in hand? This is a process which we can compute at least up to here in perturbation theory, right? Now, of course, what we see in the detector, at least let's say before entering the detector, is a bunch of stable particles. Now, given the stable particles, how will you club this particle into a jet? because our rough, naive intuition is that a spray of particles came out from the fragmentation of a single hard parton. Now, if we have to associate this bunch of particles to one of the partons, what is the right algorithm which we should pick up without violating the principles of QCD branching? So that's the whole task of jet reconstruction algorithm. And how do we club this is something which we will see. So we should keep in mind that a jet is not synonymous to parton, and there are ambiguities of this sort. Let's say in detector we see this sort of energy pattern. Just by naked eye, you can say that, oh, roughly we had two back-to-back hard partons which gave such energy deposits. Whereas if you get some isotropic distribution like this, life becomes a little more difficult. How many jets are there is something ambiguous. So whether there were multiple parton fragmentation and whether this is essentially 3-jet or 4-jet, these are the kinds of issues which we really need to understand. Okay, so essentially what I'm trying to tell you that given a bunch of particle and 4 momentum, be it at some Monte Carlo truth level or at the calorimeter level, how you cluster them into jets is the whole bunch of jet algorithm. And yeah, I will spend some 5 odd minutes for that. So those who have never dealt with jet reconstruction algorithm, at least it should be clear in your mind what is the problem, the statement of the problem we are trying to pose. Great. Okay. So let's try to do, again, relating to the basic principle of QCD branching. First of all, if we try to construct an algorithm, it should be safe from 2 things. If we add some collinear emission, then essentially that will lead to some nearby energy deposition of clusters. So that should be counted in the same jet. At the same time, if there is a sort of very small energy emission, then essentially nothing changes in the list of particles. Again, your jet definition should give you same set of jets. So, but we know that our QCD matrix elements have a divergence for very low energetic emission as well as small angle emissions. So we have to make sure that our jet clustering algorithm is really recombining the right pieces of partons together, among which this real and virtual cancellation correctly happens. Otherwise, our jet algorithm won't be IRC safe. Okay, so this is what I was trying to tell, that jets can serve 2 purposes. Like if you construct a jet reconstruction algorithm and compute jet observable, we can just measure in the lab, also can be a test bed of perturbative QCD and also non-perturbative QCD. And if we end up measuring some observable jets, we can extract specific properties of the final state as well as fundamental parameters like alpha S. And these are the things which are always done. So the IRC safety issue is something which I already addressed. That's formally put in this way, mathematical form, that you have a bunch of 4 vectors, n number of 4 vectors, a set. If you add n plus 1th, which is actually very soft, that's what tends to 0, then the outcome of a jet reconstruction algorithm should never change. That's the first criteria. The other one, which is mathematically put as collinear safe, is following. You add n plus 1th element to the set of n particles, but the n plus 1th element is almost grazingly parallel to the nth object. Then essentially you had a list of n particles and you have added the n plus 1th element, which has a very small angular opening compared to the nth one. Then the final outcome of the jet reconstruction algorithm should not change. So whatever algorithm O you construct on a set of 4 vectors, these are the basic 2 requirements it must have. Let's keep this in mind. And we already saw how the QCD is driving the conceptual development of all this. So let's see, given these 2 constraints on the reconstruction algorithm we have in mind, and we already saw that the parton branching has this Sudakov double logarithm structure, how we combine these 2 informations to construct a jet reconstruction algorithm. Okay, good. So this was first pointed out in a paper in 1977 by Sturman and Weinberg. They actually calculated what is the bond level cross section of the process, and you see you can find your favorite dimensional regularization sort of formula for this. The epsilon which is coming in this formula is actually Dimbreg epsilon. Yes. So that I will come to, that I will explicitly show. But this is just a historical slide that the first time this was written down by George Sturman and Weinberg, and they computed the cross section, which is now if you open Matt Shaw's QFT book, this calculation is properly done, and you should reproduce the computation. Okay. So now here comes the question that how those two criteria is ensuring the IRC safety. So let's think we have 3 partons in the game. Here, what we are supposed to do, that we have to club 3 hard partons, which are coming, which are shown through these blue lines, into one jet. Now, if my jet reconstruction algorithm sort of clubs 3 partons such that one of the virtual correction on one parton line is also ensuring that if you add a collinear emission of a real on-shell gluon, if it's clubbing together, then it's ensured that the sum of the cross-section of these 2 processes is finite. So let's remember again once more that the cancellation between virtual and real emission happens at the cross-section level. It's not an amplitude level cancellation. Okay, so once we ensure that we club all these emissions, one is virtual, one is real, within same jet reconstruction algorithm, call it one jet, then it's ensured, then it's ensured that the jet cross-section which we'll get by this is finite. So that is essentially telling that if you have an IRC emission of a real gluon, infrared and collinear, club it with the original partons and call it part of the same jet, then it's ensured that your jet cross-section will be finite. On contrary, let's say you have 3 such cases, 3 lines, your algorithm, some O, which tells the first 2 are clubbed into one jet called jet 1, and the third line is something which is called jet 2. In this case, the virtual emission here and the real emission falls into 2 different jets. So in the cross-section level, there won't be a cancellation. So if a jet reconstruction algorithm clubs these 2 as 2 different jets, that is not satisfying the criteria, the cancellation of a real and virtual emission. So to get finite, computable, observable, which are also measurable in lab, you better take or construct jet reconstruction algorithm which actually clubs this kind of real and virtual emission all together and measure the cross-section at one go, call it one jet. So when we saw that our criteria of IRC safety of jet reconstruction algorithm, this is what it means, that if you have an on-shell emission as an external arm of a soft and collinear parton, it clubs that parton within the same jet. Okay, so this is the idea. Good. So we sort of understood how that algorithm plays a role. And then once this was, yeah, you have a question. These are partons. So, right, we are going to measure the particles. But when you construct an algorithm, you can only do perturbative calculation on partons. So even at the, Right. And when we take, so the whole statement is when we take particles which are coming out of the fragmentation and hadronization of these partons, I better club all the particles coming from the fragmentation of this set of partons together and call it one jet. Rather, if particles coming out of these two pieces and the third line, if we club it as two different jets, then that jet algorithm can never give you finite cross-section from a theoretical perspective, so it cannot predict observables. Because if it's an observable, a theoretical formalism should give you finite numbers. Sorry? No, so first of all, let's understand that when we had this Sudakov double log structure, which we sort of spent some time understanding, the parton so when we look into fragmentation of partons, the multiplicity will populate around a small opening angle around the hard parton from which you started with, right? And we essentially know via the process of hadronization, where you also pick up some gluons, very soft gluon from the vacuum fluctuation, ultimately hadron forms, which are colorless. So all those hadrons are likely, it's a probabilistic statement, to sort of circle around. By circle around, I mean in the phase space line within a cone of this original hard scattered parton. But that slide where we are trying to make the statement that, sorry, yeah, if at the hard scattered parton, when the first branching is happening, if we are not pairing the right set of partons together, then your cross-section computation already will give you nonsense answer. That's the statement out of this. Yeah, but let's have the discussion, like even at this diagram level, if you just try to compute, I have a 3-body final state, and I want to club this 3-body within a reclustering algorithm, which one will give me finite cross-section starting from basic principles of QFT versus which one will not. Already we see that if you club this soft radiations, soft and collinear radiations in the same jet as the hard parton, that algorithm is likely to give you finite cross-section versus the other won't. Okay, so yes. Right now, no. The opening angle, it's a quantum mechanical process. So each time you create an identical copy of the original hard parton, the fragmentation, like parton showering, is a probabilistic process. Each one will sort of decay with a different angle. It's a pure quantum mechanical process. Yes.
Question about terminology and linear versus infrared. I've always understood these cancellations since it's soft gluon emission. I've always thought of it and called it infrared safety, whereas you call it collinear safety. There's another aspect, but it may be also collinear, as you indicated. There's another aspect for collinear safety, at least I've always thought, not really field theoretical, it's really just sort of operational at the hadron level. Namely, even if you go to the multi-GeV, you don't want to put in any finite PT thresholds in your seed algorithm, because then if a going from the parton to the hadron level, a gluon can fragment either into one 10 GeV pion or two 5 GeV pions, and you've got a 6 GeV threshold. You find different jets. That just sort of nuts and bolts hadronic operational that is likewise kind of a collinear, lack of safety. So maybe collinear is being used in two distinct ways here. One for the field theoretical kind of considerations, another sort of operationally at the hadron level. Maybe.
No, so here it's at the field theoretic level.
But I think there's a collinear safety consideration also at the hadron level, perhaps not as easily expressible in.
So there, at the hadron level, when we are measuring, there is always one issue of the angular resolution of our detectors. That's one aspect, which we are not talking about
I'm
right
also
now.
talking about kind of PT cuts in terms of constituents.
PT cuts in terms of constituents, which we feed in the jet reconstruction algorithm per se. It's ensuring that if I have, so that has two roles to play. First of all, if I allow, let's say, very soft PT particles to be reconstructed inside a jet, then it doesn't change the kinematics of the jets per se, but the multiplicity of the jet constituents sort of blows up.
I'm interested in the jet energy. So
Right.
the multiplicity I don't care about.
But you also care about jet substructure. Where, yeah.
Really, but right. So it depends what question you're asking. But it's really, maybe we can take this offline. Really, the utilization of the term collinear. I've always understood it as referring to avoiding PT cuts that can select between jets that look different at the hadronic level, but maybe identical at the partonic level.
What the real issue of this angular divergence is that at the parton level, if you start computing cross sections, starting from the basic principles of quantum field theory, and if you don't make your algorithms collinear safe, then you can't compute finite cross sections. So of course, I can go back to my measurement and compute a double differential cross section just by measuring yields. But then the question is, to what theoretical expression I match to? I need a finite number from that side as well. Unless you put this angular criteria in the theoretical side, coming from the principles of quantum field theory, you cannot compute finite cross sections. Yeah. Good? Okay, let's move on. So now that we sort of understood that there is a requirement of jet reconstruction algorithm fully driven by the understanding of our quantum chromodynamics theory, there were a series of algorithms which were proposed in the 80s and so on, during the days of Tevatrons, and then LEP, and now at LHC. So the purpose of this lecture is not sort of reviewing all those jet reconstruction algorithm. We will pick up one or two of them, but through those examples, we will try to understand all of these physics concepts, which we discussed for last 40 minutes or so, how they are actually realized and implemented. And then we will come to our more sort of attractive, fancy part of machine learning. Okay, so let's do it. So the first ones which were proposed are something called cone algorithm. So intuitively, if you have an original hard scattered pattern, you iterate over different opening angles and start clubbing the particles or the hadrons together. And that was like iterative cone algorithm. So if you go into literature and go for all these families of cone algorithm, you will see that people have proposed such list of cone algorithms. They are not so much in use these days, and I will tell you why. It had one fundamental problem, which is, let's say, when people started thinking about these electroweak particles and things like that, decaying into two hard patterns. So ideally, you want them to have two, like call it two jet final states. Now, if you call it what this did, the cone algorithm, if there is a virtual exchange of gluon between these two hard scattered patterns, they were tending to call it two jets. But however, if this real emission is coming from one line, this particular algorithm was reconstructing it as one jet. And surely, this two jet versus one jet, not on the same virtual real cancellation footing, is not good. This is something which we understood. Okay, so this was sort of giving us, at that point of time, not so well-controlled cross-sections at the theoretical level. And that's why people said, okay, we probably need to relook in our definitions of jet reconstruction algorithm. And that's why people propose something called recombination algorithm. So since these are actually the popular ones which are used in everyday analysis for both like PP collision, heavy ion, what you're doing, so we will just go through this once through some cartoon. So what does this tell? This tells that if I'm given a set of 4 vectors, the blobs have different sizes, denoting they have different energies. The largest blob has largest energy. And given on the direction in which these particles are flying, they have certain location in the pseudo-rapidity and azimuthal angle planes. Okay, that's trivial. Now you go on following. So you first compute something very naive, an Euclidean distance in the plane of eta and phi. Start making, so a pair will give you a distance. And then just merge the closest particles and replace it by one particle. And what does it mean replace? When you merge it, you essentially combine the 4 momentum of those 2 particles into one, just add them, and then repeat these algorithms and try to see if you put an angular threshold, how many particles inside a circular opening gets combined into one jet. This is the sort of naive idea about recombination algorithm. So if you run the cartoon here, you will see a bunch of particles will get clustered into one jet versus something which will be left out. So first intuition out of this, that if you give me n number of particles, and if you run a jet reconstruction algorithm on top of that, not all the particles get reconstructed in a jet. Some are left out. Okay, and the ones which are not good candidates to be reconstructed, throwing them away is the first role of a jet reconstruction algorithm. It's important to keep in mind. Yes?
Why not taking 3 particles? Is the program? Yes.
What do you mean? So when you compute distance, it only makes sense to compute distance between 2 points in a space. If I give you 3 points in a space, how do you compute distance?
You can make a array of 3 particles.
No, that's how not iterative branching happens. You remember our main motivation is to see whether a branching at one point of time can be merged with the original mother pattern. And a branching means one pattern fragments to 2. It's not 1 to 3 or 1 to n. Even if it's 1 to n in the final state, it happens through many different intermediate vertices. So one splitting means 1 goes to 2. That is the phenomena which we are trying to reverse engineer back and reconstruct. Okay, yes? So it has to be, the whole point is that if I give you a pair of particle, you have to give me a real number back as a distance parameter. Okay, now the construction of a Euclidean metric at least makes it some sort of rotational invariant and things like that. But is the definition of this metric parameter is absolutely unique? No. In fact, we will see soon that when we will talk about anti-KT and things like that, we will modify the definition of this metric. The whole point is, if I give you 2 particles, you should give me one number back as the placeholder for distance between those 2 particles. And based on which 2 particles are closest by the definition of your distance, okay, your constructed distance, we will do the clustering. And yeah. No, this is absolutely real space. Eta phi is actually a direction in real 3D space. In fact, if you don't see this, how it's happening. So in our sort of collider thing, this is something what we have a cylindrical coordinate system. This is our center, and in the cylindrical coordinate system, you have this angle, which is the polar angle as theta, And if you think of the azimuthal angle wrapping the surface of the cylinder, that's phi. And we have converted theta into eta through this formula, nothing more than that. Yeah, so actually when you talk about this distance, this is a Euclidean distance on the surface of the cylinder, and that's it. Okay, great.
And also, one time, you understand how collinear decay is basically transformed into a time to conical stage. Is it like some boost type stuff? At least, I mean.
So it's a delta R is a number which actually tells you that if a particle is flying in one direction, a fixed number of eta phi, what is the opening angle of a cone around that particle taking the initial direction as the axis of that cone.
But basically, start calculating from the collinear.
What do you mean? We started computing the distance between. Right.
Then you said that one is everything in the collinear. If every decay is happening in the collinear direction, then I am asking how the final collective jet structure is evolving in a conical shape.
Yeah, so it's quite easy. So if this is the original direction, there will be fragmentation like this, and this can emit a gluon. So if you think of a conical shape, where the axis of the cone is almost aligning with the direction of the original heart pattern, this is how it should evolve.
Yeah, but to take every small emission in a collinear direction, then how the final cone which we are detecting is resulting in a significantly large cone? That I am asking.
So first of all, understand that how many number of emission will happen on an average depends on what is the original energy momentum carried by the original heart pattern. That expected number of emission is a function of the energy itself. Now, every pattern fragmentation lies in a close vicinity of the mother pattern. So, on an average, you can think of what is the little opening angle multiplied by how many total number of emission. That is the expected value of what is the total angular opening of this cone. So you can give a rough number, an expectation value of what will be the total amount of the angular spread for a given number of emission. This is perturbatively, you can compute using perturbative QCD.
Can you show that part a little bit more clearly in some slide or?
Which part?
So how perturbatively it is basically you are starting from approximation, collinear approximation? And
no, not approximation. Every pattern fragmentation has a probability. And then you compute that given an opening angle like this, what is the average number of expected number of pattern splitting which are confined within that cone. That's the observable you compute. Because each pattern splitting happens with respect to its mother pattern. From there, the angular ordering comes, which Nihar is pointing out. Okay, good. Yes? Please take the mic and repeat the question.
So the idea is that you see a bunch of hadrons, and you use this algorithm to tell if that's a jet or not. Assuming you have some mother pattern and then it fragments. That's the idea, right?
Yeah, I mean,
but the output...
it's a probabilistic inverse problem question. So given a bunch of hadrons, we ask, first of all, whether it's coming from an original hard scattered pattern. If yes, what is the most probable likely kinematics of that pattern? And then another question which we will ask, what is the flavor of that pattern, which is all part of jet tagging problem, which I will come.
Okay, so the output of your algorithm tells you if it's a jet or not, and
No,
it's substructure.
the precise statement is if I am given a set of 4 momentum, the jet reconstruction algorithm will partition this set. Partition this set to tell what are the subset of particles which you can club together and call it one jet. So first the partitioning problem will tell you how many jets are there and how many number of particles which are not clubbed into any of the jets, which are thrown away. And then it will also tell you that given a bunch of jets together, what are their kinematics. This is the output of the algorithm. The input is a set of 4 vectors, and what the output of the algorithm is what I told you.
Thanks.
Okay, great. Now, there were many different algorithms which were proposed, and we will just go through the distance metric to show you that the distance metric is essentially motivated by the Sudakov double log structure, where this part is essentially delta E square by E square kind of structure and the angular structure. And then whatever is this iterative clustering algorithm was based on this metric structure. So what are popular these days? Yeah, Shomanda. Give him a mic. Okay.
Did you just say that from these, I can make out why you put the Euclidean metric in eta phi?
No. What I said that what is the motivation of bringing in this energy-dependent term in the definition of the distance between 2 particles? Earlier, if I have location of 2 particles in the surface of this cylinder, I can compute an Euclidean distance. But is that sufficient? The answer is no. This can anyone drawing cylinders and know basic school level geometry can do it. Now on top of that, if you infuse some QCD knowledge, you know that the pattern branching probability has this Sudakov double log structure. So it's not only in the angular space 2 patterns which are close by each other are likely to come from a single pattern. It's also that if there is another small energy splitting from mother pattern, you also want to combine it with the original mother pattern. So how do you inject this information in the distance parameter so that you club them together? So that's the QCD improved way of designing a distance parameter. And this is the structure which is injected here. Okay. So which one? This one? Theta by 2 because 1 minus cos square theta. So yeah, so for small angle, of course, that is true. But you also have to decide that if 2 particles are really far apart, whose mutual angle is not small, then whether or not to, yeah, that's an approximation. So wherever we saw that, so the d theta by theta is essentially d theta square by theta square, apart from some half factor. And that theta square is a small angle approximation of 1 minus cos theta. So that's why this 1 minus cos theta is entering in the distance definition. Good. So now, what is popular these days are generalized KT algorithms. What are those? So let's just make something more general. The most analytically extendable definition of the distance parameter which we learned. There were energy dependencies. So let's, instead of square, just make it to the power p, where we will choose the value of p, and then we have this angular opening, right? Now what we do is that we have something called a seed particle, the highest the particle with highest transverse momentum, which is also called beam. So you compute the distance between each particle and that seed particle. And then you try to do an iterative clustering, that if dij is less than dib, you club them together and go on until you violate the condition that dij is less than dib. And once you exhaust all the available particles, go back to slide 2, this point. So what you're left with, that when you repeat this iterative algorithm, you end up with a set of 4 vectors where the partitioning happens, that the first partition is when this algorithm runs. When this algorithm breaks down, you go back to point 2 and start making the second partition, so on and so forth. And each partition gives you a jet. That's the whole point. Yeah. Sorry? Yeah. Right. So there you saw that already the square was coming. Now, why in collider instead of energy PT is used? This is a fun question. Can anyone answer? Why eta and PT are more popular variable in collider kinematics compared to the theta and E? Everything has a direction. Boost invariance in the longitudinal direction. So when there is a pattern collision, I do my measurements in lab frame, whereas the computations which I'm doing are in the partonic center of momentum frame. Now, if I can write down observables in terms of variables which remains unchanged from partonic center of mass frame to lab frame, then my job is much easier. And that's why PT, eta, etc., which are not general boost invariant, just longitudinal boost invariant. That's, yeah? No, not energy, PT. Delta PT between two, delta R. Okay, so delta eta is a number which is invariant under longitudinal boost. Delta phi is a number which is invariant under longitudinal boost. So if you measure the distance between two particles, the angular distance between two particles as delta R square, which is essentially a distance, geometric distance on the surface, then if you do a measurement in the lab frame, versus the partonic collisions are not happening in the lab frame because they are coming with some PDFs. But you can still use the same expressions for making theoretical calculations at the partonic center of momentum frame and match with some measurement in the lab frame. Okay, good.
And also, do you count the same particle in two jets?
No. Every jet is orthogonal, means different particles are clubbed into different jets. Good. So we are sort of going towards the end of the jet reconstruction algorithm, which we wanted to understand that the general definitions of a generalized KT algorithm is of this form, where P equals to 1 corresponds to KT. Now, if P equals to 1 is KT, then of course, when you make P equal to -1, you have to give some anti-name. So that's why the anti-KT algorithm, the name comes in. And finally, when you plug in P equal to 0, there is no PT dependence, so the ordering is purely angular ordering. Now, you can ask yourself, what's the whole point of all this? Now, first of all, remember that when you plug P equal to 0, these are sort of circular jets, which are Cambridge-Aachen jets. In the eta phi jets, anti-KT jets are not perfectly circular. And how the jet shape is played a huge role, at least for run 1 LHC, for pileup removal. When all the pileup removal, I don't know if you're aware of the concept pileup, but at run 1 LHC, all the pileup removal was area-based pileup removal. Of course, we don't use that anymore. We use something called per particle pileup removal technique, something called PAPI. So that was the reason. And now the most used one, which is anti-KT, is something which satisfies all the all of them satisfies the property of good jet clustering algorithm. So we will just revisit this issue once more, that given the definition of 3 different jet clustering algorithms. You have a question? Oh, pileup is something, so when LHC collision is happening, PP, every 25 nanosecond, 10 to the power 11 protons from one side, 10 to the power 11 protons from other side is coming and smashing on top of each other. Now, all of them don't collide. Only a handful of fraction of them collide with each other, which causes hard scattering. But then there are this, even in hard scattering, there are hard scattered patterns, but then there are issues of beam remnant, an underlying event. I think you showed these concepts to them. Now, all of this can contribute to following jet. So here, let's say I have a region in the detector. I have some jets, which is coming from, let's say, center, hard-scattered pattern. So you really want whatever was the hard-scattered pattern and its branching should deposit energy here. But what happens when there are additional PP collision vertices? From those, there are additional energy contribution which lands up in the same geometric opening. Now, this is certainly a contamination of energy which distorts the energy measurement of the jet itself. Now, there are additional complications here. It's not that only contamination from one event is contaminating your jet. Since it's a very fast process, 25 nanosecond, within the time you have finished the task of reconstructing a jet, another collision has happened. So it might happen that any additional energy contamination from a different event is also populating this jet. So therefore, there are two kinds of pileups. One is called in-time pileup, and another is called out-of-time pileup. And once you have these pileups, whatever total jet energy measurement you have done for this is certainly not all the energies are coming from the fragmentation of the hard pattern which you originally aim to reconstruct. So this, if you really want to do a proper analysis, you have to remove these additional energy contaminations. And removing them is really an issue, and how to make them theoretically consistent versus how to actually deploy them and make good observables is like a huge domain of research which went to run 1 and run 2 LHC. And I'm sure I haven't read all the papers of heavy ion collision, how pileup removal is treated there, but I'm sure there are also some issues must be there. Yeah, please, Peter.
Just to relate, so the phenomenon you're addressing, the problem you're addressing is the poisoning of jet energy from unrelated processes. Now, proton-proton collisions, because there's so many protons at once, you get multiple proton-proton collisions, clearly incoherent, contributing to the same reconstructed jet.
Right.
Heavy ions, even if our luminosity is arbitrarily low, we get also pileup of a different kind. And a partonic pileup, two nuclei coming together, we have one hard scattering we're interested in studying. There could be additional hard scatterings in the same nucleus collision.
I see.
That's
an extended, larger extended object.
Versus sort of, beam pileup.
Beautiful physics.
The origin is very different.
Wonderful.
Also has to be dealt with.
Absolutely. So there must be very rigorous process to
in a certain way heavy ions.
Right.
But yes, I think it's a generic problem, but the origins are different.
Yeah. Great. Okay. So when we were dealing with in run 1, what we used to do, we try to estimate what will be the average energy deposition because of this additional contamination. And then if we know what is the exact geometric shapes of the area, what we used to do, that you estimate an average energy density times the area of the jet. Now, average energy density was what? Computed using the KT algorithm, estimated using KT algorithm. But right now we don't do it. We have a much more finer way. What we essentially do is to reconstruct a jet, look into the constituents, and try to figure out, oh, is this pileup or not? And those are the ones which we determine that this is most likely to be a pileup candidate, we remove it. So the technique has changed, but we still address the same original problem. Okay, wonderful. Yeah. So let's go in. So here it is. You remember that we have 3 classes of jet reconstruction algorithm for 3 values of P. Greater than 0 KT, equal to 0 Cambridge-Aken, less, like actually we set it 1, 0, -1 for all practical purposes. Now let's go through this. Let's read the distance parameter. Let's say you add a soft particle, right? It means minimum of this combination will pick up the soft particle first, right? If you add a soft particle, for KT, it immediately gets clubbed into the jet because this distance metric picks it up. However, adding a soft particle means its PT is absolutely an order of magnitude less than all the other hard particles present in the jet. That means the original kinematics of the jet, which is a sum of the 4 vectors of all the particles, doesn't change, right? Also, if you add a collinear particle, which means you take a particle whose angular distance with other hard particles is vanishingly small. They also don't change the kinematics of the particle. So now you go back to the definition of IRC safety, which said if you have n particles and you add n+1th, which are very soft or collinear, the original properties of the set won't change, right? So that gets satisfied for p equal to 0. Given the distance parameter, we can again repeat the same exercise. What happens in a different way is for anti-KT, where if you add a soft particle, remember p is -1. So then it actually is left out of this collection, right? So that's how the original set still remains invariant under the addition of one extra soft and collinear particle. So the distance metric, which is purely designed based on the Sudakov double logarithm structure, takes care of the fact that what properties a jet reconstruction algorithm should satisfy. Okay, this is very important, that this is not some arbitrary expression thrown at our face. There is a very well motivated reason why this is picked up, and it satisfies all the basic properties required by a jet reconstruction algorithm. Yeah, because you also need to ensure that infrared divergence safety. That's why that PT dependence is brought in the definition. Good. So now that we have like let's say PT like P 0.5-ish and let's say -0.5. Just take a number which is not 1. No, it will satisfy. So here the definition, like for all, we have to pick up, like we have, it will satisfy. Yeah. Now we who care about decay of heavy particle into other particles, which is essentially like we anticipate, oh, there can be some heavier particle in nature. Also for existing particles like W, top quarks and things like that, which goes through both hadronic and leptonic decay mode. When we make jets out of it, those jets have internal structure. Now to study those internal structure, this thing called jet substructure this goes until 1, right? The lecture, okay. So I will sort of try to finish this part a little faster. So the jet substructure is something that if there are multiple fragmentation coming from decay of more than one parton inside a jet, how do you really club them together and make informations about it? So for that, people sort of came up with different jet substructure methods. I think you talked about pruning, soft drop, right? Okay, yeah, soft drop. So why people measure jet substructure? Just to ensure that they carry, like they capture the right information that if a large radii jet has internal hard partonic structure, that is correctly captured through some algorithm which shows that a jet is not only one hard parton which is fragmenting, but there can be multiple hard parton inside a jet which forms internal structure. So for that, okay, pile up I already addressed. So for that, people sort of develop different jet substructure algorithm. So one is like prong finder, which is like a top should eventually go as 3-prong jets, Higgs and W's should go as 2-prong jet, and a quark and gluon should go as 1-prong jet. So the internal geometric structure of these 3 kind of jets should be different. Now, why in these lectures I'm worried about it? Because these are the informations which we really want to figure out using machine learning algorithms. Then there is a second class of jet substructure, which is like if there are some additional radiation is there, which we talked in great details, can there be some angularity observables? And you can see that for different class of jets, these distributions are different. And finally, groomers. Yeah, sure.
Could you go back to previous slide? Yeah, so these are cartoons.
Cartoons.
And, the way you've drawn them, the eye can, especially since you've helped us with colors, the eye can see quite cleanly. The issue is that the Quark-Gluon, it's very stochastic, and we're dealing with statistics of moderate number of final state hadrons, 20 to pick a number. And a Quark-Gluon, it's not excluded that it can look like your top decay goes to
Absolutely.
WB. So it's really, so I'm just sort of introducing an extra level of complexity. It's a matter of relative rate, and therefore kind of dependence upon kinematics and all of that as well, how well you can actually distinguish. So this looks nice and clean, but the reality, I think, has to fold in the deeply stochastic nature of jet production, no matter its origin.
Correct. But also I will say one thing. We try to address like when you say rate, it's actually the production cross-section, what you have in mind. But let's say, one can say, I give you just one piece of jet, which is most likely coming from hadronic decay of a top, and just one piece of jet, which is coming from gluon fragmentation. Now can we devise a classification algorithm which can distinguish these two? Now, of course, to make a quantitative statement, we have to make it on an ensemble of such jets, so which is like we are making an average statement on some quantum ensemble. But nonetheless, we in practice try to address this question at per jet level. Right. So when we try to define jet substructure algorithm, we ask ourselves the question that, can I just look into one jet and make any probabilistic statement that whether this is coming from a heavy part on decay versus...
Right, that's the key. I think what it boils down to is a determination of probability given a configuration,
Exactly.
not a sharp discrimination.
No.
Sharp discrimination only works if there's a very clear separation of population.
Absolutely.
Whereas these populations, they really merge one into the other.
So the posterior here is a probability.
There we go.
Good. So given that jet substructure kind of thing happened, exactly on the point which we discussed, we will come back to such classes of diagram that given an instance of jet, we cannot exactly tell, oh, this is top versus, oh, this is gluon. There is no definitive statement. There is a probabilistic statement. And that thereby, like given an ensemble of such jets, we will always, if we define a classifier on a handful of jets, we are likely to make correct decision, but also on a handful of jet, we are supposed to make wrong decision. So when we design a filter, there will always be some contamination which makes pass through our filtering algorithm, filter in the sense hard cut which we design. And that's why, depending on the value of the cut we choose, we don't define an absolute value of efficiency versus background rejection. Rather than when we float that cut, we sort of lie on a contour. And this is called, this curves, which shows that signal efficiency versus this is background efficiency, which is the contamination probability of background, is something called receiver operator characteristics. When we will talk about tagging using machine learning algorithms, this will come back again and again and again. So keep this definition of this diagram in mind, that what does this classes of diagram actually tries to tell us. Okay, so I won't spend time on this, but mass drop, trimming, etc. are just different ways to address the same question, that how probabilistically we say that something is a top versus something is a Higgs versus something is a gluon. And all of this essentially goes back to the initial construction of the representation of jet in the Lund plane. Whenever we have an algorithm, what it does is to restrict our emissions in a particular region of Lund plane. And this is a little modified definition with the y-axis being log of z theta, which is proportional to KT. What it does that the jet mass sort of appears as a straight line in this diagram, so it helps us to constrain phase space of emissions. But this is like each tagger jet substructure algorithm is essentially picking up a region in the Lund plane, and this works. Okay, great. So now, remaining say 10-15 minutes, I will give the motivation that given a set of particles, why we at all want to do machine learning. Like, could we have lived with what was developed for last 30-40 years, starting from 1977? Why do we, like, is it just writing machine learning in your grant proposal brings you more money? Is that the reason? Or there is some fundamental science-driven reason why we want to bring it? So that's the question, the conceptual question, which I want to address in the remaining 10-15 minutes, and then we will see. So when we set up a collider problem, what we essentially do, we have hard scattered patterns to particles to enter into the colliders, the energy deposits. This is what we measure. And from our measurement, we want to go back and guess the Lagrangian. So for us, at least the PP collider people, this is solving this inverse problem is one statement of what the problem we try to solve. And in here, like one can apply machine learning in many different ways. So what I will restrict myself today and tomorrow's lecture, that wherever in this process a jet is involved, why we are trying to apply machine learning and how we are trying to apply. And that I will cover the examples of what we have already done over the last 10 years or so, and what are the plans over future colliders and how we can improve as per our current understanding. So that's the goal of the rest of the lectures involving tomorrow. So let's sort of try to address this issue conceptually. We sort of now understood what a jet is. Now, what do we mean by machine learning? We always keep in mind that we are talking about complex functions, nonlinear functions, which are parametrized functions. They come with a bunch of parameters. And all we are trying to ask that this part of objects have some underlying probability distribution coming from very complex quantum mechanical interactions. If you are talking about jets at the detector level, then there is a further level of complications that this sort of particles have been smeared by detector resolution and other effects. Finally, it's a very complex probability distribution, which these objects called jets are following, and there is no first principle way we can compute it. So if we want to map that underlying complex probability distribution using a parametrized function, how do we do it? That's the main one-liner question of why we apply ML for jets. Okay, so that's the whole goal of the program, that there are jets, there are kinematics associated with it, we can measure, but we cannot solve it using a first principle forward computation. So can we map it? Can we represent it through some very complex nonlinear function? So how do we do it? So depending on the jet representation, we have to see what is, for machine learning, what is the best way to represent such data cases. We will soon see that this can be represented as an image, as a tree, as graph. What does these words mean? I will come. Then, depending on our data representation, we have to choose what kind of machine learning algorithm we want to deploy, whether it's a convolutional neural network, deep sets, graphs. Again, what do they mean? I will come later. And then depending on the final downstream task which we want to solve, we have to fix that what we are trying to do, whether we are trying to do unsupervised learning, where there are no truth labels possible, then some semi-supervised and weakly supervised learning, where the labels are there, but we sort of don't trust them accurately. Supervised learning, where we trust our label data, and then there can be something called self-supervised learning. We want to learn a probability distribution directly from measurement on the data itself. So we will come back and see that we sort of have an application of all such classes of machine learning techniques. So if you don't know the words, hold your horses. I will come and explain you each and every of the terms. Okay. So this is like sort of a test bed where the unifications of theorists and experimentalists are happening more. These two classes of people who sort of used to fight and don't see each other's faces, they have found a nice sort of cafe where they can sit together and have some chat. So why that's happening is sort of important to appreciate, and we will try to do. So how many of you have never done a single line of machine learning? Anyone? Quite few. Okay, very good. So what do we do essentially? Look, if I have a parameterized function which consists of layer, which means it's a nested function. That means if I give input some data x, it goes through one iteration of function, the output of one layer is fed to the second layer. So that's what is a nested function is. And once you do it, let's say you have some sort of output starting from the input x, and it goes through some iterative layers. That's what x1, x2 means. You give x, there is some unknown parameterized function here. The output of the unknown parameterized function is x1. And then that output is fed to the second layer, you get x2, so on and so forth. Okay. Now, how it happens, roughly, if you think of linear transformation, there is a matrix multiplication that for the nth layer, you take the output from n-1th layer, multiply by a matrix and add something. So this is just a linear transformation. Nothing more fancy than that. You have a bunch of numbers, you multiply by a matrix, add some other parameters. And when I'm talking about parameterized functions, W's and B's are the parameters. Now, our whole goal is to model a complex nonlinear function. Where the nonlinearity comes from? It comes from these activation functions. Here I have kept something called ReLU. There are a family of nonlinear functions which you can plug in here, and it will show up. And then what the core part is that if you have some sort of a loss function or a likelihood function which you want to optimize from your understanding of the underlying physics, then essentially what you have to do, that you have to compute the distance metric, the cost metric, which is something what you want to reach versus like what is the output, and you take derivatives. So this is the whole point of backpropagation, that which is all of this maths is done through some automatized software. You don't need to worry about it unless you want to really learn at the bottom of the core that what's happening. And then this is like each time you take a step, there is something called a learning rate. You compute gradient descent by computing the average of this derivative on something called a mini batch. And then each time you have done averaging over all the mini batches, computed the gradients, you change the weight parameters by a little amount. And this is the whole point of stochastic gradient descent, that by changing the weight parameters, you sort of want to get an optimized nonlinear function which reproduces or maps closest to the underlying probability distribution or whatever distribution function this highly complex nonlinear system is going through. That's the whole few lines like summary of what we try to do when we try to do machine learning. Okay, good. But now, given the machine learning is sort of defined on any arbitrary set, we come back to the same good old questions which we were pondering upon. That when we say, oh, I have a jet, I want to classify, which we were trying to do from jet substructure, now it's a more crucial question that when we set our targets, what is our target? Because here there is a very high level of ambiguity between what we actually want to tag. When we say, oh, I want to tag whether a jet is coming from a quark or a gluon, well, what actually we really want, that given a distribution of particles, what is the most likely, like probabilistically highest association of a pattern with the given distribution. So we have to be careful about labeling our distributions. Okay, and if you really want to understand the complexities of jet physics at first non-trivial step, go through this book. This one by Marzani, Gregory Soares, and Michael Spanovsky. It's wonderful book, so you should really go through this. So just trying to address, like, since jet tagging in the context of machine learning will come back again and again, what is the problem we are trying to solve? We are trying to sort of collide protons. Now, over a very short time scale, or rather distance scale, ideally there were partons. They sort of fragmented and made the hadrons. And these hadrons entered in our calorimeter and sort of deposited energy. So what is the problem we try to do? Look, first of all, we cannot solve the forward problem. Why? Because even if we can solve this part perturbatively, this is a part where hadronization happens. So that's a non-perturbative physics which we can't solve. Then how exactly a given 10 GeV pion will deposit energy inside calorimeter, that is also a probabilistic statement. We cannot solve it exactly. So what we are trying to solve, that given this distribution, which I say, let's say some pattern Q started, all the forward process happens, which is mapped by this function f, which we can't solve. And then we are trying to ask the inverse question, that I'm given a bunch of particles or some energy clusters, and I want to invert it. So this is an extreme complex problem which we are trying to solve, for which the forward problem is not analytically doable. So for this kind of classes of problem, where we have no idea how to analytically write down this sort of F inverses, we try to emulate them through nonlinear parametrized functions, which are called neural networks. Okay, so probably, like, shall I go for 5 more minutes, or I have to stop now?
It is related to your talk, that otherwise.
Okay, I think I will go on for 5-7 more minutes and then we'll stop. So now, just going back through, like, neural networks were always used in high energy physics in the sense that if you trace back early papers of people trying to do tracking, you can trace back to those papers in 70s. BDTs were always used. Even like the whole Tevatron top quark discovery, BDTs were like always used. So it's not something absolutely an alien concept to our community. But in 2014 onwards, when people realized that the energy deposition pattern in the calorimeter can be thought of an image, and the average image, which means you take an ensemble average of energy deposition patterns from different patterns. Of course, you do it in simulation. You can use these images, check the difference in the average spatial distribution of the pixel densities, and try to infer from which kind of patterns the such energy deposits are coming and depositing energy. One can apply the very well-developed branches of convolutional neural network to answer these questions. Okay, this sort of started in 2014 when the jet image papers came up, and people already tried to start comparing my jet substructure algorithms give me some performance of identifying the truth origin of a jet. How about I feed all the information into a neural network and try to see how well it can do. So this was the first time Peter Baladi, I think Michael Kagan, etc., tried to do. And it was found that it sort of works pretty well. And soon after, people realized that probably image is not the most optimal way. Why? Because our detectors themselves are not like regular grids and meshes. Each layer has different geometry, different cell sizes and things and so forth. So you just can't represent it as a regular pixelized image. But nonetheless, given such an event, you know that where the energy depositions are taking places and by how much. So the ideal way to represent such data information is by something called a point cloud. So it's a set of points. Each point, you know the coordinate, you know how much energy was released, and you just have all the information which you required to analyze such a data. So for that, people sort of started thinking, what is the best way to represent such data structure? That I have a bunch of particles. It's releasing energy in my measuring device, and I have to use this information to get best out of it. So people started thinking, whether it's an ordered set, how do I represent jet? Because remember, jet is a cluster of particles. How do I represent it? Whether it's an ordered set, whether it's an unordered set, is it a sequence, a tree, or a graph? Okay. So I will just soon finish that this sort of evolved into the modern algorithms which we use. One is the example of graph neural network, and so on and so forth. So I think this is a good time to stop today, that how this kind of algorithms are now used and how do they play a role in modern machine learning for jets, and what are the tasks which are solved today and are planned to be solved for future collider programs. How do we anticipate they're going to help us? That's the whole point of discussion for tomorrow. Okay, so this is where I will pick up tomorrow. Thank you. Any further questions? Yes.
Coming back to our discussion that eventually what one achieves is a determination of the probabilistic nature of a population. So in that context, what really is the goal of tagging? In the sense of you have a population, you've selected it by some special, maybe a coincidence channel, something recoiling from a Z, and some other features. That's what you do operationally with the experiment. What do you need to achieve in order to compare to theory? Is a probabilistic, determination of a population sufficient? Eventually, it seems you want to identify a clean population of objects whose origin you know, but that's not the same thing. So what's the goal here?
The goal is to find a very well-suited point on that thing called rock curve. Let me go back. Yeah. So from a sample, like what we compute is an expectation value, and what all this leads to is that what is the, let's remember that there are certain tuning parameters which when we float, we sort of trace this contour, right? What is the optimal cut? What is the best trend tagger, so on and so forth. So when we have a test sample, which we are using as an ensemble to extract some average over a fluctuating system, the best we can do is to determine where we set our operating points on this diagram. And once we fix that, then we go and ask instance by instance, jet by jet, that given that we had chosen a sort of working point here, if I'm choosing a jet, what is the likely probability that this came from a Higgs decay versus not, and so on and so forth. And in how do we propagate this information in any analysis is like as a systematics.
Right, but then when you come to, clearly, the closer you are to the.
Yeah, I
bottom
want
right,
to
the
get
better.
here.
But this is, rarely achievable. So then when it comes time to confronting to theory, you say, here's a population that's 85%, Higgs, but with some background, what
Right.
does one do?
They live with the fact that I'm using a particular working point where likely if I choose a jet, let's say some large radii jets with the given configuration which I have pre-selected, 85% is the probability this is coming from a Higgs versus 15% of is the probability where a gluon split it to BB bar and giving me similar configuration. Now, I have to be careful when I am using this information in the analysis that all of what I'm going to infer is also contaminated by the fact that on an average, on a bulk of statistics, 15% is a contamination. Now, how do we, now we separately go and know that what is the background, the contamination behaves like, and use it in the likelihood fitting for whatever downstream task I'm trying to do. Yeah, so that's how we actually use these numbers. Yeah.
Just to get this ROC graph or different jet observable and find it.
No, not different taggers. Taggers, or let's say classifier. The classifiers can be machine learning based. It can also be non-machine learning based, like the good old jet substructure observables, right? But the whole point is, ideally, as Peter was saying, you want to land up here. Everything is your neat, clean signal, no contamination from background, but that's impossible in reality. First of all, you want to really design classifiers which takes you more and more towards this region. But now, you know that there is a theoretical upper limit which you can never realistically go. If you land up in a like some region here, pick up a region where it comes to your sort of improvisation. But it's also important that if you choose a point here, like where you have landed, you know that on an average, what is the expected fraction of cases where your decision is contaminated by false positives. And you have to take that into account while making any statistical statement on the physics you're going to make. Yes.
Your slide later, you show a picture of a jet moving forward up to calorimeter. Next. And yeah, yes. And you made a statement that you cannot go forward.
No, what I said.
Yeah, you say, maybe you didn't say exactly that, but somehow I got the impression that you say it's not possible to go forward.
No, I didn't say it's
okay.
possible. I said I cannot exactly analytically compute the dynamics which starts from a Parton collision.
But why? Conceptually, it is possible. This is quantum field theory, right?
Yeah, but you don't know the exact quantum field theory of non-perturbative regimes.
I mean, each processes of branching is not deterministic because of quantum mechanics, but there is a probability distribution which is extremely well known.
No, it's not well known.
Why?
Because you cannot write down a probability distribution function starting from first principle, given a gluon, what will be the distributions of the kaons and pions.
Oh, but that's a separate, this is upstairs here. This is hidden in the so-called fragmentation functions.
No, the fragmentation functions are which are happening here. That's where the Parton fragmentations are happening. Here I have baryons, mesons, pions, which means the partons have recombined to form hadrons.
Okay, thank you.